This is Math 251, Sections 11, 1 and 2, Part C. We're now going to be taking the information that we've been working with on vectors, and we're going to look at two specific applications, interpreting vectors as velocity and then as force. We'll begin with velocity. If an object's motion can be described by a velocity vector v, then the object's speed is the magnitude of v. And in the two-dimensional case, where v can be described as the vector v1, v2 in standard position, the object's direction, that is its angle theta with the positive x-axis, has the property that the tangent of theta equals v2 over v1. You can see that fairly easily. If you drop the perpendicular here to the x-axis, v2 is going to be our y value here, and v1 would be this x value. And so you can see that the tangent of theta is indeed opposite over adjacent, or v2 over v1. There are two other really important relationships that we can get out of this triangle. First of all, keep in mind the length of the velocity vector. This hypotenuse is the magnitude of v, the length of v. And so we could write that the cosine of theta would be v1 over the magnitude of v. And we could also write that the sine of theta would be v2 over the magnitude of v. And if we take these two equations and solve them for v1 and v2 respectively, we get some really useful relationships. v1 would be the magnitude of v times the cosine of theta, and v2 would be the magnitude of v times the sine of theta. Those are relationships that we'll use quite a bit to build velocity vectors, so they're ones that are worth knowing. All right, so in example 1, our goal is to describe the speed and direction of the object with this velocity vector. First of all, let's just give a rough sketch. Negative 22.5i and negative 26.8j. So our velocity vector looks something like that. The speed is simply the magnitude, or the square root of negative 22.5 squared plus negative 26.8 squared. And we'll just do that on a calculator. And it's about 34.99, I'm going to call that. In whatever units the problem happens to be in. We didn't define units here, but this might be meters per second or miles per hour, or whatever our units happen to be. All right, as far as direction, we're going to use the idea that the tangent of theta is v2 over v1. So that would be v2 is negative 26.8. And v1 is negative 22.5. And if we just do an inverse tangent on that, and I'm going to note that I am in degree mode here, so I'll get my result in degree mode. And I'm getting about 50 degrees. I'm in fact round that off to 50 degrees. And we have to be careful here because, of course, with the inverse tangent, I'll always get an angle between negative 90 degrees and positive 90 degrees. I'm going to have to interpret that angle in terms of my picture, since this happens to be a third quadrant vector. So that 50 degrees is actually this angle right here. So if I wanted to correctly identify the direction, I have a couple of options. If I want to say how far it is from the positive x-axis, and if we're going to give a theta as a final answer, it always has to be with the positive x-axis, then of course I'd have to add the 180 degrees. So I could give the direction as 230 degrees, and that automatically means from the positive x-axis. The other option would be to describe this, for example, as 50 degrees south of west. Or alternatively, this would have to be a 40-degree angle, so I could go with 40 degrees west of south. Any of those would be acceptable answers for direction. All right, example 2 puts us in the three-dimensional case. We'd like the speed of an object with this velocity vector. And of course, again, speed is just magnitude. So we're just looking at the square root of -1 squared plus 4 squared plus 2 squared, or the square root of 21. And I'll just leave that one exact since it's not so bad. As far as direction for a three-dimensional vector, the vector itself is just going to be the best way for us to describe the direction. In terms of an angle, there's so many different angles with respect to, for example, the x-axis, since we're now three-dimensional, that I can't really define it that way. There is something called a set of direction cosines that talks about the cosine or the angle with respect to each coordinate axis, but in fact it doesn't really give us any better information, in my opinion, than the vector itself. So I may ask for the speed given a three-dimensional velocity vector, but I won't ask for the direction other than the vector itself. All right, in this third example, if you're driving 50 miles per hour in a direction that is 20 degrees north of due west, express the velocity as a vector in standard position, assuming usual orientation. So north would be straight up. All right, 20 degrees north of due west. So west is over here. We'd be looking at a velocity vector like that, where this angle is 20 degrees. We also know that the speed is 50 miles per hour, so that means that the magnitude of this vector is 50. So I'm going to go back to those two little equations that we derived from our triangle for V1 and V2. Magnitude of V times the cosine of theta, and then times the sine of theta. So I'm going to say that V1, magnitude V cos theta, would be my magnitude of 50 times the cosine of, and I do need to be a little bit careful here. The angle has to be the angle with respect to the positive x-axis. This 20 degrees, of course, is not. So I'm going to have to use its supplement, 160 degrees, as my theta. And again, just making sure your calculator is in radian mode. That's just something you can do on the calculator. And I'm getting about -47 degrees. Or excuse me, -47. V2, magnitude of V sine theta, would once again be 50 for my magnitude. And this time I need the sine of 160 degrees. and that comes out to about 17.1. I could put this as negative 47.0. I did round to 1 decimal place. I just got negative 46.98. So rounding to 1 decimal place went to negative 47. All right, so my vector has components negative 47.0, comma 17.1. Notice that that makes sense. That would put us in the second quadrant, which is exactly where we're supposed to be. All right, let's take a look at a three-dimensional case. As this mentions, the fact that it's not possible to describe the direction using a single angle means that we're going to have to work a little bit harder for this one. We have an ascending airplane traveling at a speed of 100 miles per hour in a direction 70 degrees north of due east, but also ascending at an angle of 15 degrees. Find a vector to describe the airplane's velocity. My strategy here is going to be to get the direction right first. Once I have the direction correct, we know that there's an easy way to make the magnitude be whatever I want it to be, in this case 100, right? We just make a unit vector and multiply by 100. So getting the direction right has got to be my focus. After that, I'm going to be good. So let's make a quick sketch here. All right. Keeping in mind this is now three-dimensional, my y-axis here is still going to be north. And let's see, that would mean that the x-axis is east. And I want to go 70 degrees north of due east. So I'm looking at a vector kind of over here. With this being a 70-degree angle north of east. Okay. I'm not going to try to get that vector to be any particular length right now. As a matter of fact, I'm going to end up with having it be length 1, because all I'm going to do is I'm going to write down this vector in the xy, or excuse me, yes, in the xy plane to simply be the cosine of 70 degrees and the sine of 70 degrees. So right now that vector has a magnitude of 1. All right. I now need to let this ascend at an angle of 15 degrees. So I'm going to imagine taking this vector and literally tilting it up 15 degrees. I made a little right angle in here, and that is a 15-degree angle. It's probably a little bit more the way I drew it, but I needed to make it look perpendicular. So we'll label it 15 degrees and be good from there. Once again, right now, I'm not concerned at all with the length of this vector. All I need to know is its direction. So, since this point is directly above this point, I know that the cosine and the sine are the x and the y values. Those have not changed. But I do need a z value to go with this. So z, this vertical here, is what I'm going to need to figure out. And again, I'm just going to use a little bit of trig to do that. Since this is 1 and this is z, that from 15 degrees would be opposite and adjacent. So I'm going to be able to say that the tangent of 15 degrees is equal to z over 1. Or simply that z is equal to the tangent of 15 degrees. Okay, I now have a vector that's in the correct direction. In order to get the actual velocity vector, I'll turn this vector into a unit vector and then multiply it by 100. So let's work on that. My unit vector is simply going to be the given vector, or the vector we figured out. I guess it wasn't really given. divided by its magnitude. Oops. And that's just something that you can do on your calculator. And there we go. I just popped off to do the calculations so you didn't have to watch me push buttons there. And so I've got these values, simply dividing each of these by that radical in the denominator. Because I want a speed of 100 miles per hour then, I can say that my velocity vector is just 100 times this unit vector. And you'll notice that I did keep, in my case, 4 decimal places. I kept a significant number because I knew when I multiplied by 100, I was going to still need some accuracy. So I now would have 33.04, 90.77, and 25.88 for my velocity vector. All right, we will pause there and pick this up in the next video.